An alternating current is an electric current that reverses its direction at regular given intervals in an electrical circuit. Alternating currents are generally used in household appliances and communication signals carried on conductive wires. Alternating currents are linked to topics taught in Math 141 and 142 by the maths surrounding complex numbers, impedance, and phase relationships. On the right, we have the classic example of a sine wave in AC circuits. The complex number j is expressed as the square root of -1. It can be shown in two forms, rectangular and polar. On the bottom we have the 4 formulas to show how to convert between rectangular and polar forms.
Understanding the use of complex numbers in AC circuits. The reason why complex numbers are used throughout circuit analysis is because when there is an AC source rather than a DC source powering a circuit, components like resistors, capacitors, and inductors all react differently. All these components create an opposition to the electron flow. This effect is known as complex resistance, which is the summation of resistance and reactance. Impedance. The impedance is the total resistance of resistive and reactive elements within a circuit. The voltage formulas for resistors, capacitors, and inductors, respectively, are the following formulas. These can be manipulated using Euler's formulas, which are the following, and as a result, we end up with a formula for complex impedance, which is Z equals R plus J omega L minus J over omega C. Also, the magnitude of impedance is then given by the following formula.
How do these components react with AC? In a resistor, the voltage is in phase with the current, therefore impedance equals resistance. In a capacitor, the voltage lags behind the current by phase minus 90 degrees, therefore the impedance equals the reactance. This equals minus J over omega C as shown in the top right hand image. In an inductor, the voltage leads the current by phase positive 90 degrees, therefore the impedance equals the reactance, as shown J times omega L, which is shown in the bottom right hand image. Phase relationships. In an AC circuit, capacitors and inductors produce impedance, which means that the current in the circuit does not peak at the same time as the voltage in the circuit. The difference in the period of the waveforms between these two is called the phase difference and is expressed as an angle. In a capacitive circuit, the phase difference is negative as current leads voltage, and in an inductive circuit, the phase difference is positive due to voltage leading current. In the image below, you can see the voltage and current represented in the angles as well as the impedance and reactance. And the formulas below that are the polar forms of voltage, impedance, and the angle.
So here's an example. We're going to calculate the complex impedance for the circuit below. This is known as the RLC circuit. Here in the top left we have our circuit, and this is how we work out the total impedance. You add the resistor plus the reactance of the inductor minus the reactance of the capacitor. Once we work everything out, we've got our magnitude, which is it changed to polar form. We have 141 ohm at 45.03 degree. Some of the engineering applications of RLC circuits can be seen in devices such as this audio amplifier. The dials you are adjusting are actually connected to frequency filters, which are made up of different combinations of RLC circuits. Thanks for watching.